Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 1, Anova for completely randomized designs. Okay, so just as a reminder, we're working on a situation where we have our subjects who are randomized into one of T treatments, and then we observe a response Yij, which is the response for the jth person in treatment I. And you could ask yourselves, are all of these treatments performing similarly, or is there a difference? Is there a treatment effect? So if you were in the situation where you wrote out the model Yij equals mu I plus epsilon ij, right? So you have the true mean for each of your T treatments. Then you could write your null and alternative hypothesis as I have in this first line. If you write out your model Yij equals mu plus tau I plus epsilon ij, in this case, you're saying there's an overall mean plus some treatment effect. And in this case, you would write out, are all of the tau 1 to tau t's equal to 0, meaning there's 0 treatment effect from the overall mean. So if you have this overall mean, did you do better or worse compared to that? So what's that treatment effect? In reality, when you do this test, it's exactly the same, whether you parameterize your model, as I did in the first line, or the second line. It doesn't really matter which one you use. The actual carrying out of the statistical test is similar. Okay, so we're going to calculate an F statistic by taking your sum of squares treatment divided by the degrees of freedom of the numerator, t minus 1, over your sum of squares error divided by n minus t. Okay, that's the same as finding the MS treatment divided by the mean squared error. Now, if the null hypothesis is true, that's essentially saying the treatment effect is no different than random error, right? So then if it's true, this is going to follow, your test statistic will follow an F distribution where the degrees of freedom on the numerator are t minus 1 and the degrees of freedom in the denominator are n minus t. So if I plot out the F distribution, looks like a skewed right distribution that peaks at 1. I can set up a rejection region, reject HO, and we're going to just say alpha equals 0.05 right now. And then I can set up a failed to reject region where 1 minus alpha is 0.95. Now, real quickly, there is nothing, absolutely zero things special about 0.05. Just because your alpha level or your p-value is 0.049999 or your p-value is 0.050001, there's not anything special about 0.05. But at the end of the day, we need some value to determine when we think that the treatments are different enough to say that they're different. And this all comes down to like how many people are in your sample, how many treatments are you looking at, did you have a good study design? So there's nothing special about a p-value being smaller than 0.05. It's just that the smaller and smaller your p-value is, the more evidence you have against the hypothesis. But we're just using this cutoff as just a starting point to help us make those decisions. But essentially, anyone could make a p-value go to get very, very small. You just take a larger and larger sample and your p-value will get smaller and smaller because you'll be dividing by a bigger denominator. Okay, so to calculate the p-value, you can use an F table if you'd like. I prefer to use the functions in R. I find them to be easier, but overall, you're going to find the probability that your test statistic, right, is greater than the F distribution, right? So essentially, you're going to say, if I find my test statistic, I'll draw it in a different color. Let's suppose my test statistic falls over here. So if I get my test statistic, essentially, I'm going to say, I need this area under the curve, right? So essentially, I'm going to say PF of your test statistic, and your degrees of freedom, 1, are going to equal the t minus 1, the numerator degrees of freedom. Degrees of freedom 2 is going to equal n minus t, right? And I'm going to say lower tail equals false, because I want that upper tail probability in R. Okay, so essentially we're finding the area of under the curve, assuming the null hypothesis is true, of being beyond our test statistic, so being further in the tail. Okay, in general, if our p-value is less than alpha, right, that means that our test statistic is very, very large. Okay, so let's choose another color. So suppose my test statistic was beyond my critical value, then the associated p-value is going to be very small. That's going to be my p-value. Okay, if your p-value is very small, you're going to reject HO. If your p-value is very large, that means you don't have a lot of evidence against the null hypothesis, and you're going to fail to reject. But I probably can't stress enough that there's nothing special about your alpha level. It's a predetermined level, right? Your p-value is just trying to tell you how much evidence do you have against the null hypothesis. But at the end of the day, when you're doing this test, you're really saying, if you reject HO, you're saying at least one of the treatment means is different from the rest. And if you fail to reject HO, you're going to say there's not a significant difference in the treatment means. So, you know, if these were, if you were trying to test the efficacy of 10 different vaccines, you would want to know that those 10 different vaccines, you'd be asking yourself, are any of these vaccines more effective at protecting people against a disease or not, right? And so if you reject HO, you would say, oh, this particular vaccine or that particular vaccine, at least one of these, it has more protection against some disease. Whereas if you fail to reject HO, you would say, you know what, all these vaccines are equally effective. And it doesn't matter which vaccine that you get. All right, I hope you learned something today. I'll see you in the next video.